Okay, so how's everyone doing this morning? How did it go with the fourth assignment? So, so as you can see, the difficulty of the assignments has been ramping up. I don't know if you've noticed that. That's intentional, but so just in case, well, if you're in this situation, you may not be here today, but maybe you'll listen to the video. So just in case you're thinking, the next assignment is going to be at a level that's above what you're capable of, the next assignment's actually fairly easy and fairly short. And you'll learn everything you need to do the next assignment. You'll learn that in class today. So you can start it today. I guess you'll get a little bit more time because there's a holiday on Monday, so I'm not going to make you stay up until 8 o'clock Monday morning on Thanksgiving weekend. So you'll have a little more time to do it, but you don't need the time because it's short. You can knock it off before you leave on Friday and have that done. And the week after that, we won't have an assignment because that's the week that we have our midterm. So a little bit more on that later. Okay, and I'll post a solution in case for the people who are interested. I'll post a sample solution for assignment 4, so you can maybe use that to figure out why yours was getting different numbers than mine was. So one thing I guess I should get, so it's, yeah.
In the first week you said if we had enough time to do 11 assignments, we would not run off.
Yeah.
Do you think we'll have enough time?
I think we'll have enough time to do 11 assignments. So you'll get the best 10 out of 11 on the assignments. Yeah. I was thinking maybe like Wednesday morning, so that would really mean Tuesday night. So you have a day to get back from wherever you are and sort it out. But you also really don't need the time. You can easily do it this week. It's one of these cookie cutter assignments again. Part 1, Part 2, Part 3, Part 4. In fact, only 5 parts and 1 bonus part. So you get a little break for a while. About the assignment, I guess, I'd like some feedback. What did you guys think? Yeah?
It spent a couple hours to just wrap my head around what the whole bundle of functions was doing, but once I actually started, it was just more understanding syntax.
Okay, good. And understanding syntax isn't fun either, but it's something that you do once early on in your career, and then you're set for life. Yep. Sorry.
I'm looking for more description for a question, but sometimes I know the question it is, but I know where should I start, how to start. I know it, but I don't know how to convert it to a code. That's the problem to start.
Yeah. So that's what we're working towards, is this ability to take a fairly vague, fairly vague criterion or a fairly vague feature request, convert that into, internally in your own thought processes, convert that into how you think it should be done, and then convert that into code. So a lot of these things, it's easy to know what should be done, but then the conversion to code is difficult, and for some other people it's difficult to figure out exactly what should be done even, but if you told them exactly what could be done, the code would be easy. You guys have to be able to do all of these eventually. Yeah?
I felt like the assignment, the question was weirdly written. I felt myself just staring at the screen and what exactly is being asked.
Okay. So all 4 parts, or?
I think one of the reasons was because in the written set of words where I felt like it should just be smooth, solid programming.
Yeah. So the problem with making it one solid program is there is some learning objectives to this, and one of these is learning to define classes and create objects and so on. And so if I just said, you know, I mean, really the whole question is basically question 3, where you make this application, and the rest of that is surrounding that. If I just said make this application, then most people would not even try and use classes because it's something new and they'd rather just use something that's familiar to them. So I kind of forced you, shoehorned that in. Maybe not perfect, but now you know how to use classes. Yeah.
Yeah, I found it, the question a little bit ambiguous in the sense that when you said create the list and that sort of stuff, so I created a skeleton of the whole process and then class it. So I just kind of set it aside. I said, okay, fine, I'll be good on Sunday. And I didn't get any sleep last night when I realized I created all the lists and tuples, and then realized that I had to create objects.
Yeah.
And so all the search queries, the set command, and to iterate through the code now it doesn't apply for objects, and it kind of threw everything to.
Yeah. Yeah. So, that strategy of development where you develop a skeleton that maybe doesn't have all the features, or in this case isn't implemented using exactly the way it's supposed to, and then converting that into a usable program. That's a common strategy, but it does run into these pitfalls that if you may make decisions early on that are not quite compatible with what needs to be done later. But it's still not. I mean, it's still a good way to learn. It's just it may take a little longer, and then doing the rest on Sunday night is never a good idea. But you guys know that. Yeah.
I found the order of the question weird because you need to learn the library first before you can do the question.
Yes, but if you don't have any, so the order asks you to define the objects first and then define a function that loads the library. But if you haven't defined the objects yet, then what are you going to load the library into? I guess that's my question. So you could load it into an array, but then you'll have to go back later and redo that code to load it into a list of objects or whatever. So, yeah. So how to connect the ordering of what? Okay. Yeah, so the sample code does one thing and you need to make it do another, and it may not be obvious immediately how to do that. Really the purpose of the sample code is to just hide the fact that, to show you how to look up tracks and albums, but the real trick is to hide the weirdness of traversing a whole hierarchy of directories, and so that you don't really have to understand how that works at least. Yeah. Mm-hmm.
If something went wrong, it would load it all and then have to wait a good solid 5 minutes depending on what was happening before I can even check.
Yep. So 5,000 MP3 files is a lot, but that's what I had 10 years ago. That was basically a collection of CDs that I ripped to MP3s. So it's not a huge collection. I mean, it's about 400 CDs. So not huge, and certainly something that you would have to deal with. Now, for testing, you're free to take 20 of those and stick them in a directory, and just test on those for a while until things are up and running, and then put the rest of the files back in. Okay. Yep. Yeah, so there's a few albums that have problems. That's the danger of working with real data. You'll always have files that have errors in them, don't load properly. That's why we wrap these things up in a try except, so that those things don't crash your program, but you won't be able to load them. Yeah, there's like a dozen or so, or maybe more, depending exactly on how you handled things that don't exist. So some of the MP3 files, for example, don't have a talb field. So they don't define what album they're from. And so if you blindly try and look at the dictionary to see what album they're from, actually you get a key error because there's no key in that file called talb. You'll get a key error and you won't be able to load the thing. So some people won't load those at all. Other people may have set it up so that that defaults to a blank thing without causing an error, and then they all go to a different album. It depends exactly how you handle it. But the TAs have been instructed to be generous with error handling. So, you know, if you missed out, if there were like, I don't know, 50 or 100 or so albums which didn't load for various reasons like that, that's not a problem. But if there's 5,000 albums that didn't load, like all of them, then that'll be a problem. Yep.
You said before that like the reason you gave us that sample code was so that we could just load in from the files without needing to know how the code worked. But I found that you basically had to know how the code worked in order to make it function. So giving us the sample code kind of pointed us in the right direction, but I'd rather kind of not get code I didn't know how to use.
Okay, so the thing that I wanted to avoid you having to know is how to traverse a directory and all its subdirectories. And that's that strange-looking for loop that uses os dot whatever. And I didn't want to get into all the details of that. So yes, you do need to know that when you load an audio track, what you get back is this dictionary, in fact, we'll talk about them today, that has these various keys in it. But that's pretty much all you need to know. Yeah.
The issue with the sample code is, since I didn't know exactly how it worked, I didn't want to mess with it, because I thought I'd like
Break it? Yeah.
That's just us.
Yeah, so in general, don't be afraid of breaking things. So, you know, go ahead, play with things. If you break them, you still have the original sample. Same thing with your assignments. Don't be afraid of tweaking them. I just recommend, you know, when you have something that works, copy it into a subdirectory and save it, and then go ahead and start hacking away at it. Then if you totally break it, you can always revert back to the old version, or even submit the old version if you're running up against the deadline. Yeah?
For assignment 3, it says graded on page when I open it, and you also comment there's no grade.
That's probably the same issue as before. They haven't released the grades yet because there's some TA who's lagging, and so I guess they'll all get released soon. Okay. So today I want to talk about sets and dictionaries. So what are sets and dictionaries? Well, these are data structures that are available in Python, and they're available in many languages, and they're available in the libraries of many languages. So you'll find them in C++. There's the whole standard template library. In Java, there's the Java collections framework. In C, you have to rely on some third-party libraries. They're not in the standard library, but there's still plenty of third-party libraries. And in Python, they're so critical somehow that they're almost, they're not exactly part of the language, but they're definitely part of the standard Python library. So before I tell you about them, the first thing I should tell you is that sets and dictionaries, they don't give you really any functionality that you could not do yourself just using lists. So you'll see that all the things we do today, you could have also done them using a list. And it wouldn't be hard, but what sets and dictionaries buy you that lists don't is that they're really fast at what they do. So there's a few operations that they support which are really, really fast. And when I say that, I really mean that the time that they take to do things is independent of the amount of data that you're storing. So this is a really powerful idea. So it says that, for example, if I make a set, and I make a set with 1 million elements, then that's not really any difference in terms of performance or it can support operations just as fast as a set with 20 elements. So for instance, I make a set that contains 1,000,000 things. I can ask you if something is in that set in time that's independent of that. So it doesn't matter if there's 1,000,000 things, 1,000,000,000 things, 10 billion things, 1,000,000,000,000 things. Sets can test if something is in them in time that's independent of their size. And think about lists or arrays. If I make a list that has 1,000,000 elements and I ask you if something is in the list, well, the only way to know that is, well, in Java you can use the in keyword, but the way the in keyword works is it just goes through the list, one element at a time, checking to see if the thing you're looking for is in there. If it is, it returns true. If it gets all the way to the end of the list, then it returns false. So that means, you know, if the list has 1,000,000 elements, it has to look through 1,000,000 different things before it returns false. If the list has 10,000,000 elements, it has to look through 10,000,000 things, and if it has 1,000,000,000, it has to look through 1,000,000,000 things. So for example, if you have a list with 1,000 elements versus a list with 1,000,000 elements, it takes 1,000 times longer to look through the list with 1,000,000 elements. And sets don't have that issue. Sets, you'll see, it doesn't matter how big they are, you can look through them as quickly as you want. So let's just start hacking away. So sets are like arrays. You have several different ways of defining them. And one way is what are called literals. And the same way you can make an array by putting square brackets and listing the elements in the array, you can make a set, except you use curly braces. So here's a set that contains 1, 2, 3, A, B, C. Okay. Now before I hit enter, can someone tell me what a set is? So forgetting about Python, forgetting about languages, if you've taken a course in discrete math or finite math, they sometimes call it, they may define a set mathematically. Anybody tell me what that is? No? So, well, you'll learn in 1805, if you haven't learned already, a set is an unordered collection of distinct elements. So there's two words there. Unordered, well, collection, we sort of know what a collection is, but distinct is the other key word. So if I look at this set S that I just created, there it is. So one thing you may notice about S is, well, the elements are in a different order than I specified them. So I specified 1, 2, 3, A, B, C, but actually in this set they seem to appear in the order A, 1, C, 3, 2, B. And if I iterate through the set, they come out in that other order. Okay? So this highlights the fact that sets are really unordered. So you stuff things in them, and you can't rely at all on the order that if you ask for the things back, you can't rely at all on the order. So they're not like lists or sequences or arrays where the order is really important. For example, I can't ask for the item at position 0 in a set. It just says doesn't support indexing because there's no particular order. If ever you did something like that, that's almost surely a bug in your program or a fact that you don't understand what sets are supposed to do. Yeah?
So, is it following a specific formula for how it puts the stuff in the set? Or is it just
There's no formula, no guarantee at all. So I might run the same code again and the things might be in a different order the next time. Okay? So unordered, that's the first important property. And the other important things about sets is that they contain distinct elements. So let's see. Let's try and make a set that contains 1, 2, 3, A, B, C, D, and then 1, 2, 3 again. And if I look at that set, well, each of 1, 2, and 3 they only appear once. So a set cannot have two elements inside it that are equal. Okay? It's just not allowed. If you try and put them in, it just won't put them in. Okay? And equals here really means that the two elements, if you say, you know, the reason we couldn't put 1 and 1 in is because 1 equals 1. Same reason we couldn't put, for example, 1 plus 1 in because 2 is already in there. Okay? So, in fact, no, you can't. Yeah, in fact, here you see, for example, some of the differences. Here's a set that contains A, B, C, D. Here's another set that contains A, B, C, D, 1, 2, 3. And notice the ordering is different in those two sets. So again, to highlight the fact that order doesn't matter. Yep.
So when you put in the 1 plus 1, you didn't get it because there's already 2, but if
Yep.
2 wasn't there, would it be printed out as 1 plus 1 or 2?
No, it would appear as 2. Right? And that's just, again, that's just an order of operations thing. We don't really think of comma as being an operator, but it is. And so the comma operator has a lower level of precedence than the addition operator. So 1 plus 1 happens before the commas take hold. Okay. All right. So questions there so far? Order, yep.
So there's no way of telling which order they'll be in, it's just purely random because of the code?
There's no way of telling, and if you care, then you shouldn't be using a set. Okay. Yep.
There's another way of making just something random, like if you push S again, would it appear in the same order or just a different order?
Let's see. So it happens to come out in the same order each time, but no guarantees.
So not always, but it will.
Sometimes. But again, if you rely on that, you're sure to run into a problem at some point. Okay. So if you care about the order, you shouldn't be using a set, or you should be using a set and something else. So, and that happens. Sometimes, in fact, I think even on the assignment, there'll be times when you would like to store your data maybe in a list and in a set. Okay, so what are things you can do to sets? Well, you can check if something is in the set. For example, I can ask, is C in the set S? The answer is true. Is X in the set S? The answer is false. Is 4 in the set S? The answer is false. And is A in the set S? The answer is true. Okay? So that's an operation that sets support really, really fast. So again, doesn't matter if I have a set of 1,000,000 elements or a set of 6 or 7 elements like I have here. That's really fast. And we can kind of convince ourselves of that. Let's say big set is equal to, and I'll show you another way of making sets at the same time, range 1,000,000. Okay? So if I look at the length of my big set, it contains 1,000,000 elements. And if I ask if 42, 43 is in my big set, the answer is there just instantaneously. So it's really, really fast. Doesn't matter how big you make your sets, they'll be fast. Really, the limiting thing here is probably how much memory you have in your computer more than anything else. Okay, so back to our little set. You can add and remove things. So I can say s.add, maybe we'll add 4. And now 4 is in the set. And I can remove things, s.add 1. And now 1 is gone from the set. And again, these are two operations that are very, very fast. That's not the case with lists. If I try and add or remove things to lists, there's really only one place that I can efficiently do that. That's at the end of the list. So I can append things to a list. You've seen that method before. There's also a remove operation for lists, but it's terribly slow. It basically has to go through the list looking for the thing you want to remove. It removes it, and now it actually has to make the list smaller. So everything that comes after the thing that you've removed has to be moved back one position in the list. So basically, removing from a list of 1,000,000 items means you'll have to search through a bunch of items and also move a bunch of items in a list. Okay. So these are the three operations. The three set operations that are fast are add, remove, and the in operation. Yep.
Are you limited, right now you're just putting like integers and just one byte type, almost like the little box you talked about, or you're using large objects in the
No, I can put anything that I want into a set. So there's no problem there. Most things. I'll warn you now, though, that if you make objects and you put them into a set, you may run into problems. Until you know a little bit more about what you have to do, what you have to add to your objects to make them work with sets. So if you just create a new kind of object, put it in a set, it may not behave exactly the way you want. Even if you redefine the underscore EQ method, it still won't work the way you want. So there's a little bit of danger. So if you do that, be warned. You need to know a little bit more than we're going to learn today. So to really hit home this, or really drive home this point that these things are faster, we can just do a really simple experiment. And it's one that we actually did on day 3 of this class. So remember, we opened this dictionary and we split it up into words. And there's this big list of words in there. And we did this little experiment where we looked for, well, two things. One is we looked for palindromes. And remember, palindromes are words that are spelled the same forward and backward. And so that was looking for the words in the word list. If, when you reverse them, that's what this does, if that's equal to the word itself. And very quickly we got a bunch of palindromes. 130 palindromes in this dictionary. And then we decided we wanted to look for anonyms. So remember what anonyms were? No? So what was an anonym? It's like a palindrome, so it has to do with what happens when you reverse the word. So, yeah?
It's a word reversed isn't another word.
Yeah. So an anonym is what you have, is a word that if you reverse it, you actually get a word. Not the same word necessarily, but you do get a word. So for example, every palindrome is an anonym because, well, if a palindrome is a word and I reverse it, I get itself, which is also a word, so it's an anonym. But there's a lot more anonyms than palindromes. So for example, we saw pat and tap were a pair of anonyms. So one is the reversal of the other, and each one is a word. And so to get the anonyms, we use exactly the same piece of code. We want every word W in the word list if we reverse the word, then we find that reversed word in the word list. What's that? If it's itself, it's also an anonym, because then it's a palindrome, and palindromes are anonyms. And then we ran that code, and we waited a while. So I got tired of waiting on the first class, and then I did something that made this run a lot faster. So let's think. We've just learned about sets. Sets store a bunch of things, a collection of things that are distinct, and it's really fast to test if something is in the collection. So how could we use a set here? So this is too slow, right? This is unacceptably slow. So how could we use that here? Word list? Well, that will make a set, and that set will have one element, which is a giant list. So we don't want that. But more, just at a higher level, what is it we're trying to do here? Yep. Okay, so I would like to make word list into a set. And if I do that, so that's easy enough to do, so I can say word set is equal to the set that I get by turning word list into a set. If I look at the length of word set, it's a little bit smaller than the length of word list. That's probably because some words appear twice in the list with uppercase and lowercase. Different, but they've all been lowercase when we loaded them, so that the duplicates get removed when you make them into a set. And now where would I use that in this line of code? Well, let's take a look at what's happening here. In this line of code, this is a for loop that is going to assign W to be every single word in word list. Okay? So this line of this loop that we've made here is going to execute 97,723 times. And each time the loop executes, it's going to do this if statement. And this if statement reverses the word. That doesn't take long. But then it checks if that word is in the word list. Now, most of the time it's not, actually. And so most of the time, it actually has to go through the entire word list all the way to the end, comparing the reversal of W to every single element in that word list until it's done. And then it has to do that again for the next word W, and so on. Okay, so if we just think about this for a few seconds to understand why this is taking so long, well, we have 97,000 or so words, and each time we take one of those words, we look through the whole word list again. Well, there's 97,000 words in that word list. So if we count the number of times we're comparing two strings, the reversal of our word and something in the word list, it's 97,000 times 97,000, which is that many string comparisons. So let's figure this out. There's 1,000, 1,000,000, 1,000,000,000, so about 9.5 billion string comparisons. That's why this is taking so long. Okay? So for every word, we reverse it, and then we compare it to every other word in the word list. So that gives us about 9.5 billion string comparisons. And you guys, most of you have bought computers at one time or another. How are computer speeds typically measured? Yep. In gigahertz. So do you know what a gigahertz is? A gigahertz, yeah. Yep. It's a billion. times a second. So hertz measures how long it takes to do a cycle, essentially. And so megahertz is millions of cycles, and gigahertz is billions of cycles. So, you know, this is 9.5 billion, and even fast computers can not even do string comparisons in 1 or 2 cycles. They actually take, you know, dozens of cycles to compare 2 strings. So really, I mean, we're doing a number of operations which is way more than this thing can do in a second. In fact, it's way more than it can do. We sat there and watched it for a minute, so it's more than it can do in a minute. So we're not going to get around having to look at every word in the word list. If we want an exhaustive list of all the anonyms, we have to look through every word in the word list, but we can make it faster to check if the reversal is in the word list just by using a set instead. Remember? Sets are very fast to check if something is in a set. You can do it in time that's independent of the size of the set. Done. Okay. So there's 708 anonyms. There they are. Okay, so let's just word set. Okay, everybody get your timers ready? Done. Word list. It's longer to do it using a list than a set. Yeah.
Why? It's so much faster.
Okay. So hopefully now you're convinced that these things are important, right? It's not a big. This is not a really complicated task, finding all the anonyms, but you know, it's a question of whether we can do it quickly or not. And this is an example where even if you only wanted to do this once, if you only ever needed to find a list of anonyms once, it's still faster to say, this is taking too long, go back, rewrite the code to use sets, and run it again. You'll be done before this original process would be finished. Okay. All right. So questions about sets? Yes? Yep.
So this would use a search function where it looks for the ABC instead of the index?
Okay, so if you're using sets, they're very specific. So they're really add things, remove things, check if things are in the set. So there's not really a notion of searching other than checking if something is in the set. So you don't ever get anything back from a set search other than the answer true or false. It's in the set or it's not in the set. And so the next thing we'll look at is dictionaries, where they do what you're talking about, which is you search for things based on their key value. Okay. So sets are, they're very fast at what they do, but they don't do a lot. They just store elements, you can add, remove, and you can very quickly check if things are in the set. Now, at some point, we made a program for testing, what was it? It was the Collatz conjecture. Anybody remember that program? Yeah. So it was, we can, oh dear. I don't think it's called Collatz. September 18th. So one of the things we were doing, so this is all uninteresting. So this Collatz conjecture says that if you start with any positive integer n and you repeatedly look at it, and if it's odd, you multiply it by 3 and add 1, and if it's even, you divide it by 2. And if you do that, then the claim is you'll eventually get down to 1. And we wrote a little program that tested this. So this little bit of code checks this for one value of n. So it repeatedly either divides n by 2 if it's even, or it multiplies it by 3 and adds 1 if it's odd, and it'll keep doing that until n is equal to 1. So it'll do it forever if the Collatz conjecture is not true for n. And then we wrote this other wrapper around this that tested this for all the values of n. Okay. So can you think of a way maybe that you could use sets to make this faster? Yep.
Every time you do a comparison, if it's not 1, you add the number is to the set, and you keep doing that. And so what you do first is you check if the number you're using in the set, if not, then see.
Okay, so there's this set of numbers n for which the Collatz conjecture is true, right? And we think it's all of the integers, but we don't know that. That's what we're testing here. So for example, Collatz is true for the integer 1. It's true for the integer 2 because 2 is even, so we divide it by 2 and then we get 1. And it's true for 3. 3 goes through some cycle where you say 3 is odd, so multiply by 3 and add 1, you get 10. Divide by 2, you get 5. That's odd, so then you get 16. Divide by 2, you get 8. And then 4, then 2, then 1. So it's true, we keep testing it for these small numbers. And if ever we come across a number that we've seen before, well, then we know it's true from that point onwards, right? So it's true for 4, for example, because 4 is even, we divide it by 2 and we get 2, and it's true for 2. Because at that point we can continue, we know that whatever we did to get from 2 down to 1, the same thing will happen again. So we could try and use a set to make this faster. And so what we'll do is we'll make a set, we'll pass that into our function, and we'll say, So the Collatz conjecture is true for 1, and we'll say while n is not in S, we repeatedly do that. And when the Collatz conjecture is true, we add n to S. Okay. Okay, it says Collatz takes 2 arguments and only 1 was given. That's because we forgot to pass this new argument that we just defined in there. Okay, so now we have a version that uses a set, and, well, we didn't save the old version, so it's hard to say if it's faster or not. My guess is it should be a little bit faster, but there is one drawback to using this, and that's that we have this set that's getting bigger and bigger and bigger. Eventually, we'll basically just saying that, well, if we're doing the Collatz problem, if we're trying to see if this number that we're starting with will eventually finish at 1. If it ever gets to another number that we know eventually finishes at 1, then we're done at that point. So if it gets to a number that we already know the answer for, then we're done. Okay. And there's, you can do tweaks to that. Okay. So questions about sets? Good. So you know what they are and you know when to use them. When you need to store a bunch of distinct things, and you need to know if something is in that set. And don't be afraid to use a set, even if you also need to store your data somewhere else. So, maybe you do need your data in some specific order. Maybe it has to be sorted, or maybe it has to be the order that it's given to you. But don't be afraid to also store it in a set if you need to do a lot of searches for that data, or a lot of tests to see if stuff is in there. Okay, so the other thing I want to look at today, the other data structure I want to talk about, are dictionaries. So dictionaries are a lot like sets. So they're unordered. The data that you store is unordered. And dictionaries store a set of things called keys. Now the main difference, and when I say set, I mean all the things that implies. They're not ordered and they're all distinct. But they actually, with each key, they associate a value. So just like a real dictionary, like those big books that your grandparents have on their bookshelves, they have a big list of words. And what do you do with those dictionaries? Well, you look for a word because you don't know what it means, right? So you know a word, but you don't know what it means. So in the dictionary you go, you find the page that has that word on it, and then right beside that word is its definition. Okay? So that dictionary maps words onto their definitions. So the keys are the words, and the definitions are the values associated with these words. And what's special about those big paper dictionaries? What makes them efficient for looking up definitions? Yeah? What's that? They're ordered. So they store the words in an order which makes it fast for you to look things up in them, right? It wouldn't be very helpful if the dictionary had an unordered collection of words, and if you want to know a definition, well, what you do is you start on page 1 and you see if that word is on page 1, and then you flip to page 2, and then somewhere around page 4000 you find the word that you're looking for. That wouldn't be very useful. And the same thing is true of dictionaries in Python. They're stored in a specific way so that they're very fast at matching. Given a key, they can give you its definition or its value very quickly. So there's a few ways to do those things. So If you want to define a dictionary, or a dict for short, that's how you do it. Now I have an empty dictionary. And interestingly, they look a lot like arrays. So I can say, for example, d at 1 is equal to 52. Now I see that my dictionary has this key 1, and the associated value is 52. But what's interesting is I can index these things not just with integers, but with anything. So here I index the dictionary with the string me, and I add the value, or I store the value Pat Morin. Okay. And if I say, well, what's d at me? It's Pat Morin. If I say, what is d at 1? It's 52. Okay. So when you print them out, they show you these things as pairs, usually the key, colon, the associated value, and then it's a list of these things. So a set of these pairs, really. Okay. Now the keys have to be unique. So for example, if I say d at me is equal to Pedro Gomez, that doesn't store two different keys, me, one that points to Pat Morin and one that points to Pedro Gomez. It actually just changes the value associated with the key me, because the keys are supposed to form a set. Each one should appear only once. Okay. You can also delete things or remove things from a dictionary. And the notation that you use for that is a little bit funny. So you specify which key you want to remove. So 1 disappears from the dictionary. Okay. So let's, think of maybe an application that this might be useful for. Well, it's any time you want to associate keys and values. So, for example, let's take, I think I've got an old 0. So here's a list of companies on the NASDAQ stock exchange. And so this is a CSV file where the special character is this vertical bar. So we can load this file up and split it using that. So let's do that. So maybe we'll just look at one of those. So now we've got this file all loaded and split up. We have this array of lines. Let's see how many. 2,734. And each line is itself an array. The first thing is the stock ticker symbol for the company, and the rest is information about the company. So the second piece of information seems to be the company name, and then there's a bunch of other stuff. And if you knew anything about stock markets, you might know what this means. I don't know. So what would be a useful way to store this in a dictionary? So let's say you're watching CNN or whatever your favorite news channel is, and across the bottom you see this, there's this constant scroll of these types of letters here. Little 4-letter things going across, and then often there's a price beside them. And maybe there's even, that price is colored differently. Maybe it's red if it's going down or black if it's going up. And one of them really catches your eye. Like you think, okay, for whatever reason, this thing looks really good. I want to know what company that is. I've watched it go by 10 times. Its price keeps increasing. And I want to know what company that is, but all I have is this 4-letter thing. So how would a dictionary solve that problem? Yep. Yeah. So we would like to make a dictionary, and where the keys are these 4-letter things. And then the values, well, maybe the values could be the company name. Then you'd be able to look up the company name. So let's say, we'll say for line in lines, we'll say stocks at line at 0 is equal to line at 1. Okay? So line is going to go through all these different things. And line at 0 is this code here, AAIT in this case. And line at 1 is this thing here. So to our dictionary, the key we want to use is line at 0, and then the value we want to associate with that is line at 1. So we have 27,000 values in stocks, or 2,700 values in stocks. So somebody give me the name of a stock, ticker symbol of a stock. What's that? ACMC? FC. Atlantic Coast Federal Corporation, common stock. Another one? POT? Nope, not in there. This is, I think it's it's NASDAQ. So whatever's on the NASDAQ list. BWI? DWI. Nope, not in there. AOL? Nope, not in there. Most of these are 4 letters, so here's one I know. Google.
Is there any performance issues doing a sort of a dictionary before doing that?
You can't sort a dictionary. So if we look at this thing again, if we look at stocks, do you see, well, let's, for S in stocks, so let's print this thing out. There's no discernible order in there at all, right? This is the order that this thing happens to have these things stored internally. Certainly not alphabetical order by the keys, and the keys are the things it looks up by, so you can't sort dictionaries. If you want to do something like that, then you would say, list of stocks is you take that dictionary and you turn it into a list this way. Okay. So now you have list of stocks. There it is. So if you want sorted order, then a dictionary is not for you. Put it in a list and sort it. Okay. So a few things about dictionaries. So collections like list and set, we can test if something is in there. But what does it mean to test if something is in a dictionary? So for example, we've still got this dictionary that has all the stocks in it. So I could ask, is Goog in stocks? The answer is true. I could ask Panera Bread Company, Class A common stock. Is that in stocks? What do you think the answer is? False. So dictionaries sort of treat themselves as a collection, but only of keys. So Panera Bread Company is a value that's stored in the dictionary. The key that's associated with that is PNRA. So PNRA, that is in stocks, but Panera Bread Company, Class A common stock, that's not in there. And, yep.
You would do like the value for stocks at PNA in stocks with that.
How do you mean? So,
Like the same format as when you're assigning it to stocks.
like this? So what do you think the answer there will be? So what's stocks at PNRA? It's that thing, right? So is that in stocks? False. So it's really just these key values that you can check there. Okay. And like a dictionary, like a set, it's super, super fast to do these things. So adding things, so setting the value for a key, that's really fast. Deleting a key is also really fast. And getting the value that's associated with the key is really fast. So basically, all the operations that do this are really fast. And another one which you find yourself doing a lot is this. First checking to see if a key is in there. And really the reason that you find yourself doing that is because you want to avoid this error here, which is, not in stocks. You want to avoid this error. This key error. So you'll find a lot of code for dictionaries that looks like this. You know, if some key is in stocks, then x equals stocks at. So you'll write a lot of code like this when you use dictionaries. This just makes sure you're not going to raise an error if the thing you're looking for is not there. Okay. So I'll warn you again, for now, don't use your own objects as keys in dictionaries. Okay? So like sets, there's some special stuff you have to do with your own objects if you want them to be able to go into sets or to be used as keys in dictionaries, but you should feel free to use them as values. Okay? So there's no problem using them as the thing that's stored alongside the key, but the keys themselves, don't use your own objects. Probably you want to use strings or numbers or something. That's more likely. So a couple of things. What if I wanted to work the other way? What if I knew the company name, but I wanted to know its special code? So how would I do that? So make a new dictionary where things are reversed. Okay, so let's say stocks 2. That's going to crash because I haven't said what stocks 2 is. So now I say line at 1, I still haven't defined stocks 2, okay. Stocks 2. And then say line at 1 equals line at 0. So now if we look at stocks 2, so there's stocks 2. It contains all the same stuff, but the order is reversed. So for example, LSB, whatever common stock, that goes on to LSBI. Now, is this a particularly useful dictionary? Okay, so I would like to know the stock symbol for Google. So that's in stocks 2, right? Wrong. Yeah, you have to know the exact thing. And so that's a feature of both sets and, sorry, stocks 2 is where I would want to look, but it's also not there. It's a feature of both sets and dictionaries that they only do exact searches. So for example, even in stocks, oops. I somehow erased stocks. So even in stocks, sure, Goog is there, but if I get the case wrong, it's not there. So it really only does exact searches. So this is something you have to, be aware and be careful with. Is if you're putting stuff in dictionaries or in sets, and you want to know if stuff is in there, you really have to, if it's strings, you probably want to convert it to lowercase, both when you put it in the dictionary and the thing that you search for in there. And other things you may want to change in ways that make them canonical, but they're totally useless for things like, if I want to look up Google's stock symbol, really not helpful that way. Is there anything we could do to maybe make this work a bit better? Yeah. Okay, so we could make everything in the dictionary lowercase. Let's try, let's try that. So for the stocks dictionary, that would just be this. So now, you can empty a dictionary this way. So now all of these things are in lowercase. So that's helpful. And then when you search for something, you would also put it in lowercase. What if we wanted to solve this other problem of reversing the, being able to look up the stock symbols for a particular company? Yeah?
You could make a function that takes in your search and includes a list of things that contain with your...
Okay. And is there a way we could use a dictionary to do that? So I could, for example, one way to search for something is, let's say my word is Google. Then I still have these arrays. So company names is line at 1 for line in lines. So there's just a list of the company names. So I can certainly say, do a search like this that says, I want the name for name in company names if W is in name.lower. Okay? So go through each one of these names, convert it to lowercase, and then check if W the thing that I'm looking for is in there. So let's see what that gives us. That gives us the one result with Google in it. And we can try changing W to be, I don't know, give me a search term. Yeah. Ink, oh, that's going to be a good one. Lots of companies with ink in the name. Dynamic. Lots of those. Now, is this fast? Or if this was a really big set, would this be fast? No? Yes? Well, I'm not going through the list many times, but I am going through the whole list, right? So one search means looking through the whole list. And that's the kind of thing that that dictionaries avoid. So let's see if we can use dictionaries to speed this up. Okay, so we'll be lazy about this. We say open NASDAQ listed.txt read split lines. Okay, so this is just the opening this file. And now what I want to do is make a dictionary that maps words in company names onto stock symbols. But we might as well make our other so for lines, symbols. Okay, so now we've loaded this all up. Now I'd like to make a dictionary that maps words, the words that appear inside company names, and maps them onto stock symbols. So, seems like I want to go through the list of all the companies. So maybe, again, for line in lines. Now, the company name is line at 1. So what do I want to do with the company name? So for example, the company name is Google Inc. Class A Common Stock. What would I like to put in my dictionary? What's that? Yeah, so I'd like to split this line. So the words in the company name is name.split. So now I have a list of words in that company name. So one of those words is Google, for example. So what do I want to associate in the dictionary with the word Google? Yep. Okay. So with Google, I want to associate Goog, its ticker symbol. So that's something like, oops, I shouldn't do that. Let's call this thing name words. Name words at, well, let's say for W in words. So W, for example, will be Google at some point. And I'll say name words at W is equal to line at 1 or line at 0, the company name. Okay? So let's see what that does for us. Typo there. It's bad news when you get an error on the first line of code. Good. So if we look at name words, what have we got? Well, let's try name words at Google. There it is. Now let's try name words at Inc. Is that right? There were a lot more companies than that with Inc. in their name, right? So let's rethink this. So what do? We say name words at W is equal to the company's ticker symbol. So at some point I run across a company whose name includes the word Inc., and so I say name words at Inc. is equal to this company's ticker symbol. Some point later, I run across another company like this, and then I say it's equal to this ticker symbol. And then it looks like here, the last one that I came across was a company whose ticker symbol was ZN, and overwrote that. So actually, what we'd like is to store, rather than just one ticker symbol, we want to store a list of ticker symbols. And here's a common recipe for that. So what we'll do is say if W is in words, then name words at W will add this ticker symbol. And otherwise, it means it's the first time we've ever seen this word in a company name before. We'll say name words at W equals a list with only one item, and it's the company's ticker symbol. Let's try that. Name words. Okay, and somebody give me a keyword in a company name. What's that? Book? No key name book. Let's try one we know is there just to see if that works. Goog. Inc. Want to give me another one? Online. 3 companies with online. If you want to know what they are, you can look in here. What's that? Bosk. No? Did I get that wrong? Ah, that's why. Better online solutions. CNET. ChinaNet Online Holdings. It's not what you would have thought, maybe. JRJC. Okay. So now we have this this dictionary that you can give it any word, and it will tell you the ticker symbols for the companies that have that word in their name. And we'll leave it at there for today.
Is there any difference between, so when you do if he is in the dictionary to do something, is there any difference between just doing the dictionary key and then doing a try and accept? Like, is either more efficient?
I wouldn't say either one is really more efficient. And it really depends what you want to do. I wouldn't say one way is more efficient than the other. Just try and accept, typically you use as sparingly as possible. So you never want to take like a big function that crashes half the time and just rapid fire around it because you don't know why it's crashing. But so if you can avoid them, you generally try and avoid them. So. And otherwise, but both work.
You told us for all the other assignments how many people handed them.
Yeah.
So personal curiosity, do you know how many handed this one in?
I haven't looked yet. So I wanted to do a bunch of things before class today, but 20 minutes before class I realized and came back here. That's why I'm here.
You got the 20-minute workout.
Yes.
And it's not why you didn't post today's assignment, right? This week's assignment.
It's not posted yet. No.
When? Cool.
It'll be posted probably before lunch today.
Oh, great. Thank you.
Yeah.
I think you said agree.
And then agree.
Oh, we could run the sample code and get everything run through without getting reading the function.
Yeah. So in the sample code, there's one place